Good afternoon. I think we can get started. Thank you for coming to this seminar on life cycle assessment. It's my pleasure, great pleasure, to introduce the speaker of this seminar, Dr. Ming Xu, from U of Michigan. Dr. Xu is an associate professor. Actually, he has a joint appointment at the U of Michigan in both Department of Civil and Environmental Engineering and another Department of Sustainability. So it's a really cross-disciplinary kind of appointment. He obtained his bachelor and master degree from Tsinghua University years ago, and a PhD degree from Arizona State University. Since after that, he joined U of Michigan as an assistant professor to start with. And in recent years, has received a number of awards, including this very renowned Faculty Early Career Development by NSF of the US. And currently, he is a chief editor of the journal. Some of you may know this journal, the Journal of Resources, Conservation and Recycling. It's one of the leading journals in this field. And I just learned he took up the post of the chief editor. The journal has an impact factor of 3 or something, and between 2 and 3. Now the journal has an impact factor of 5 point something. And so that's already some achievement in this regard. And he has been elected to chair of this Golden Research Conference, Golden Research Conference on Industrial Ecology in 2022. That's some years later. So the chair already established at this point, a few years before that. And again, it's a title, it's a long title, but the subject of this his seminar is on life cycle assessment, but using different approaches for methane data. And we are really looking for this kind of topic on both data and life cycle assessment, an important and very popular topic in our days. And, everyone please join me to welcome Dr. Xu for his seminar. Well, it's a little bit of confusion here. We are supposed to take a...
Thank you very much for the introduction, Professor Lee, and it's my great honor to be here. This is my third time in Hong Kong, but the first time at Hong Kong, University of Hong Kong. So it's a great honor. I want to, as Professor Lee said, the title of my talk is really a mouthful. It's a lot of words there. I hope I didn't scare some of you away. So I want to essentially, the keyword here is life cycle assessment. This is, I'll introduce you what this means later. And I don't think in Hong Kong you will have many people working in this area. Maybe 3 or 2 people in this field. But I think it's really important field of research that a lot of places are really need this kind of research. So I hope I can convince you that today. So first of all, I want to just again introduce this journal, as Professor Lee said, which I'm currently editor-in-chief, Resources Conservation and Recycling. This is a journal, what we call a multidisciplinary journal. It does not belong to a specific field, a discipline. It's what I call a question-oriented journal. So we're looking at any research that addresses questions related to sustainable management of resources. And it doesn't matter what kind of method you use or what discipline you come from. So we have papers from the engineering community. And we also have papers from the social science community. So we have a lot of environmental behavior studies in the journal. Sustainable supply chain as well as from the business management point of view. in order to, these days, so many journals coming up every day, and we publish a lot of papers. So in order to help our authors to make their papers stand out, we have implemented some initiatives in the past couple of years. One of the things I'm particularly interested in doing is to have what we call guaranteed social media coverage. So any accepted paper in this journal will be guaranteed to have a social media coverage in Twitter, LinkedIn, Facebook, and also WeChat. There's a code there. If you are interested, you can scan it. I think we have more than 6,000 people now subscribe to our WeChat platform. So if you publish here, you get access to a much broader audience than your traditional audience. Right? As part of this journal, we also organize an international conference series called International Conference on Resource Sustainability. So next one will happen in Australia in next year, July. And the topic of the conference is cities, anything related to cities. And the abstract deadline is July 15th in 2019. So, and as you can see, we have a lot of engineering folks and also social science folks as well. So I think, I hope we can receive some submission from you guys. Okay, so in terms of my research, what do I do? Well, a nutshell is that I'm interested in looking at the environmental implications of industrial systems, like a technology, like products we use. Why? Because if we can understand the environmental implications of those things, can help us to guide the technology and policy development for sustainability, like how can we achieve the best environmental outcome and avoid so-called unintended consequences. So in our research, we use life cycle-based approaches, essentially life cycle assessment as a specific tool. Life cycle assessment, or LCA in short, essentially tell us what happened for a product system from cradle to grave, from raw material acquisition to end of life. And during this whole process, what kind of environmental impacts you have. So this is what we call life cycle assessment. This gives us a holistic picture, a system-based picture about a product system instead of just one phase of that system. Life cycle assessment is a methodology, but I think what's more important is the life cycle thinking. It's a way of think things differently. So essentially, we in life cycle thinking we try to consider the entire life cycle of a product to evaluate its environmental impact. Right? This so-called life cycle includes the raw material acquisition, processing the materials, manufacturing for the product, and transport and use, and after the use, recycle, reuse, and eventually disposal. The whole process of a product system. Right? So what difference can this kind of thinking, life cycle thinking, make? Or why do we need this? Right? So just give you an example. So these days, plastics seems to become enemy of the humanity. Right? Everybody, every country, every organization is kind of fighting with plastics. So this is actually not the first time. It happened like in 1970s already in the Western world, developed countries, using alternatives, mostly papers, to replace plastics was a symbol of environmental literacy back in 1970s in developed countries. The main criticized the same back then. Plastics take much longer time to degrade in the environment, so that it causes a lot of human ecosystem health impacts like this. Right? But from our life cycle point of view, this impact is only happens only at the one last stage of the product's life cycle in their life. Right? So if you're looking at the whole life cycle of plastics versus alternative, for example, a paper, right? Paper bag versus a plastic bag, they can both provide us the same functionality, carrying the same amount of stuff for the same period of time, right? But behind those two different products, similar products, similar products, there are two entirely different industrial systems. Right? For paper, we start with trees, of course, and then tree being cut becomes a pump becomes making a paper, have a plastic paper bag, and then after the use, end of life treatment, the incineration, landfill, or other processes. A life cycle of plastic bag is entirely different. It came from oil extraction, refinery, and it becomes resin made plastic bags, and then after in the end of life, landfill, incineration, or just throw it away. So in these two different life cycles, at each stage, we use different resources, different amount of energy, and generate different types of emissions, waste. Right? So if we think about the life cycle of those two different things, their environmental impacts are entirely different, even though they can provide us the same functionality. Right? So this was a paper published in 1991 in Science. Right? They did a life cycle assessment. Look at the paper and versus plastic products, which can provide the same functionality on the same functionality basis. To look at the life cycle, energy use and also air emissions. Right? So this dark blue bar represent energy use and air emissions for same function-based paper products. Right? So from this result, it's pretty obvious that paper is worse than plastics, right? If we consider the whole life cycle of the two different things. Second, if we consider energy consumption, or we're concerned about energy consumption and air emissions, right? But this, of course, does not tell us paper is worse than plastics. It just tells us if you think those things from different angle, different perspectives, you will have different answers. So the real answer of which one is better in terms of environment, it really depends. Depends on your, from social science point of view, stakeholders, right? You have different stakeholder, you will have different preference. Some groups might be more concerned about energy use. Some group, they might just concerned about the impact on the species ecosystem health, right? So, at University of Michigan, I teach a course just related to this. Every student in my class, if they took the course, they will be able to do this, right? But, back then you can publish this in the science journal, but now, you cannot even get an A from my class, right? So the field actually has been advanced really dramatically in the past couple of years, and also, in terms of life cycle thinking, let's just recap. We essentially just take a product system into our parts and trace it back to the whole life cycle, or in business world terms, supply chain, from raw material acquisition, processing, and until the end of the life. And at each stage of this life cycle, we have resources consumption, energy consumption, and also we have waste emissions generated, right? So, so from life cycle point of view, we have to know all those details, all those impacts, resource consumption, energy consumption, waste generated at each stage of the life cycle product. Then we can understand its true environmental impacts, right? So this life cycle thinking essentially is commonly known as footprint. So from the medium, you heard about carbon footprint, water footprint. This is a water center. So footprint essentially is life cycle thinking, just a more scientific term, right? So there are many applications for life cycle thinking in environmental policy making. So first, life cycle thinking can help us to identify those key processes in the life cycle of product which contribute the most environmental impact. Right? If we know which processes are making contribute the most environmental impact, that's where we want to improve in future, right? You have more rooms to improve there. So this is essentially we can guide the technology development for improvement in terms of environment. Second, it can essentially just tell us a true environmental impacts of consumption of particular types of product or technology. just to avoid shifting environment burdens, right? By shifting environment burdens, just to give you another quick example, electric vehicles, there's no tailpipe emissions, right? But all the emission has been shifted to the upstream stage of the life cycle, electricity generation. Right? If you use coal to generate electricity, your electric vehicle actually could be worse than internal combustion engine vehicle. Finally, if we consumers, individual consumers like you and me, and also institutional consumers, government, universities, they know the life cycle environment impact of the stuff they buy, they purchase, then they can make informed decisions to choose products that are better for the environment if can fulfill their function need. So there are many policy examples in the real world apply life cycle thinking. At the global level, international level, the IPCC assessment report, most recent version, AR5, has a specific, just one chapter dedicated for calling for attentions on so-called embodied greenhouse gas emissions transfer between the world regions, country from country. This so-called embodied emission essentially is a life cycle concept. So at the national level in EU, they have this thing called a product environmental footprint, which regulates some sort of products sold on the EU market that has to disclose their so-called environmental footprint, which is a life cycle concept. In the US, we have this Energy Independence and Security Act, which regulate how much, for example, specifically how much subsidies you can receive from the government if you produce renewable energy, right? So some of those subsidies require you have to reduce your life cycle emissions compared to a gasoline baseline or some other baseline. In China, they also have the eco-design by the Ministry of Industry and Information Technology, Gongxingbu, which considers the whole life cycle of the product when you design your product at a very early stage. So at the company level, there are multinational companies these days. Social responsibility is a big thing for them, and part of their social responsibility is to release or disclose and monitor their carbon water footprints. And to do that, you have a lot of different ways, methodology to do, and they are all based on life cycle thinking. Right? Like this greenhouse gas protocol, which is mostly widely used method to measure companies' carbon footprint, which is a life cycle based approach. Right? So that's the background of the whole field. And in terms of me, my own research interest, I'm interested in understanding how does the consumption of technology, consumption of products drives production and also the environmental impacts from the whole life cycle point of view or footprint. And the goal, of course, is to use our research to help decision makers or policy makers to make a better informed environmental policy. Right? So I have two levels of interests. One, I'm interested in consumption of products at a micro scale. What I mean by micro scale is essentially specific products, right? For example, this water versus that water, right? Produced by different companies. And there we use life cycle assessment as a main tool. And at the micro, also interested in the micro scale studies, which look at the consumption in general, right? For example, consumption of water versus consumption of computers. It doesn't matter, what kind of computers you have. There we look at the larger scale at the sector level, right? So in that case, we use a lot of economic models as well. So in terms of environmental impacts, we also define, in our work, we also define environmental impacts very broadly. It includes resource consumption, including water, energy consumption, energy use, and also pipe emissions, waste. Right? So if you do a life cycle assessment, as I mentioned, I have two different levels of interest. So today I'll just focus on the first one, the micro level, where a specific product level environmental impacts, life cycle impact assessment. So if you do a life cycle assessment, you essentially first just look at this, understand this product, and see what's the processes of making this product from the raw material acquisition to end of life, right? And for each stage, because the industrial system we have today is very complex. Even for a very simple product, you can have very complex supply chain or life cycles, right? So at each stage, you can further divide process into sub processes as well, right? You can do this over and over again, and until you have a better picture of the whole system, right? And also because our industrial system is very globalized today, so many of those processes happen in other places, right? Not in the same region or country, right? So in terms of process, we do a life cycle assessment. First, you define some goal and scope, like the science paper example we used. If your goal is, or your stakeholders' interest is energy consumption, right? Your goal might be only looking at energy consumption, right? But you have another stakeholder, your goal might become climate change, greenhouse gas emissions, right? And the scope, which means what are included in your life cycle, right? Ideally, you want to include from raw material acquisition to end of life, but in some cases, depending on a specific research question, we might not need to do that. Just a piece of that whole life cycle is enough. And then we do something called inventory analysis. After you have defined the scope of your study, how many pieces you have in the life cycle. At each piece, right, what's the resource input, what's energy input, what is the emission output. So that's what we call inventory analysis. After inventory analysis, what does those emissions, what does those resource consumptions mean? What's the impact on the environment? We have an impact assessment to see how much of that emissions mean to the environment, to ecosystem health, to human health. Right? So at this stage, you get things like 2 kilogram SO2 emissions. Right? For example, that's from life cycle something. Right? And at this stage, you convert that 2 kilogram SO2 emissions into indicators that can measure human health, ecosystem health, or resource depletion. Like in human health, we use daily disabled adjusted life years as an indicator to may have an average collective measure of the impact on human health by many different types of emissions or waste. For example, here we might not only just have SO2, but also have CO2, nitrogen emissions as well. Right? There are two types of life cycle assessment. Right? The first type, broadly speaking, is empirical life cycle, what I call. We have, first you can do a life cycle of a very specific thing, identify those so-called hotspot processes where you can make further improvement. Right? Second, you can do a so-called comparative life cycle assessment to compare two or multiple products which can serve the same function but have distinctly different life cycles, like the paper versus plastic example, right? And so there are actually a lot of studies doing in this area to look at the different water treatment technologies, life cycle environment impacts. Consequential LCA, that's another area which closely relates to economic modeling. Combine LCA with economic models, consider market response, what happened, what would the environment impact be if you make change for a particular technology, right? So the second types of LCA studies are focused more on the methodology and the data, right? Like the second group, people help the first one do their job better, right? So in the past, I do a lot of things here, did a lot of empirical LCA studies in transportation, energy, water areas. But now increasingly in the past couple of years, I increasingly moved to this area. I want to, dig into the methodology and the data issues and help, my colleagues in the other area to do their job better. So as you can imagine, LCA is very data intensive. So we have mainly three steps to do a life cycle assessment, and the most important two pieces are very data intensive. So this you have get a lot of data from different industrial processes. This you need to know a lot of data on impacts of human health, ecosystem health because of release of some sort of emissions, right? So traditionally, those data are coming from primary sources. On-site investigation, you go to the factory, go to the plants to take the measurement. You do a laboratory test, right? You do a questionnaire, surveys, and then a literature review as well. In literature review, the data, secondary data you get are also from primary sources, right? So then you can imagine this process can be very expensive and time-consuming, right? So there is this missing data issue in a lot of LCA studies. In a lot of cases, you just don't have that data, right? There's nobody know that data, right? You don't have the resources to go to the factories to do the survey to have that data. What do? You make assumptions, right? Which brings a lot of uncertainties. Secondly, you just say, I don't have that data, I don't consider that process, right? So, this motivates me for my research. Do we have another way, alternative way, which is more efficient, cheaper, more faster to get those data if we don't have access or enough resources to get those data? In the past couple of years, data science becomes very popular and had a lot of advancement in the past couple of years. So here, in the past couple of years, I also try to utilize their new technologies, new techniques from data science to help people do LCA. So in those two pieces that I mentioned earlier, which has a lot of data required in LCA, I try to find suitable data science techniques to help people to estimate those data instead of going to factories, going to the sites to collect those data as a primary data source. So here I want you to, for the rest of today, I want to introduce you two recent examples of our recent work. One is looking at this inventory data, another looking at this impact data using two different approaches from the data science. So the first one is to use something called link prediction to look at the estimated inventory data. This was recently published in Environmental Science Technology. This work was mostly done by my PhD student, Ping Ho, who highlighted there. I want to give her full credits. So in the life cycle inventory, what you have essentially is a matrix like that, or a table, giant table. In this table, each column represents what we call unit process, a process of making a very specific thing, like make a paper, for example. So, and then each row represents an input to that process, resource input, energy inputs, and also output. Emission outputs, waste outputs, right? For example, we have a column like this, which is make 1 unit of paper, 1 gram paper. On average, we know to make 1 gram paper, we need 2.3 gram of pump, 1 liter of water. So this was just random numbers, doesn't mean it's true, right? And also 1 gram of paper needs to generate 0.8 liter of wastewater, something like that. So to do a life cycle inventory, we have to essentially just to fill this table out, right? Fill each cell with a specific number, right? Like this, some numbers we know, some numbers we don't know, right? That's in the past. So, this giant table essentially is also a network, right? What we call bipart network, in which you have two types of nodes. Those squares might represent the columns, unit process, make a paper, make a glass, etc. Circles might represent a specific type of resources used, for example, water, energy, electricity, etc. Or emissions, SO2, CO2, for example. So this table here essentially can be represented like a graph, like this. So if we don't know a specific number in this table, essentially that means we don't know whether there is a link exists between those two nodes, right? Or more specifically, we don't know whether there's a link exists, or we also don't know if there is a link exists, how large that link is, how strong that link is, right? So this, in this way, we can translate our missing data, filling out the data in that table, that task, into a task of estimating a link in a network, right? So estimating or predicting, what they call predicting a link in a network is a branch in this network science, a subfield in physics, in data science. What they do essentially giving a partially observed network. You observed some area of that network. There are other areas you don't have time or don't have resources to observe, but you use whatever you observed as information to help you to predict the connection, linkage patterns in those areas that you haven't observed. Right? For example, if you know there are links like this, and here from 4 to 6, there might be a link, there might not be a link. We just haven't observed. But instead of going to the field to actually observe, you might, based on whatever you know already, to predict whether there is a link or not. Right? This is what actually Facebook use. If you add me in Facebook, they will recommend me, for example, Professor Lee. You might also know Professor Lee, right? Of course, they use very sophisticated algorithm now, but the principle is the same. You based on my network versus your network, look at the patterns, look at the similarities, and then recommend friends you might know. And that means, essentially, is a link in a network. Right, and same thing happens when you go online to shop, right? To buy things that will recommend you. You might also like those other things, right? So this same principle can be easily applied in the same our question. Estimating link exists in a network, bipartite network. But our task is actually more difficult than Facebook, because they only need to know whether Bob knows Jane, right? Whether it's 0 or 1, whether there is a link or not. But we actually need to know not only just whether there is a link or not, we have to know how strong that link is, right? Because everything here has a number, right? So that makes our task more difficult. What we did essentially we pick a relatively complete lifecycle inventory database that a lot of people have worked for so many years to collect, right? This giant table, and then we intentionally pick a process and intentionally randomly pick one piece of data and remove it, right? And say that we don't know those data. Our goal is to recover that data, right? And then we develop link prediction models. We have an estimate of this data, to replace that original data. And then because we intentionally remove that data, but we still know that data, right? So then we compare our estimation with the original data as a way to measure our model's performance, right? And if we validate a model which can recover data, missing data very well, then we can use this method to estimating those data that are actually missing, right? So we used something called ecoinvent, which is perhaps the most comprehensive database, lifecycle inventory database exists today. It was developed in Europe. The original data set has 11,000 columns representing 11,000 types of different unit processes. But they have some processes are very similar, like producing electricity in Germany versus producing electricity in Switzerland, right? So we make some treatment of that original data and shrinking it into a data set of 2,500-ish columns and 7,000 ish rows, which means we have 2,500 different types unit processes, and 7,000 something resource use and emissions. Right? And then we use this data set as data we already know, and intentionally remove one piece from each process and recover that. Use our try to find a best link prediction model to recover the missing data. Right? So just give you a flavor of what this data set includes. This is a specific process in this data set, machine operating diesel, less than 18.64 kilowatts on one money. So it's very specific, right? And they also have some other processes like same thing, machine operation diesel less than same kilowatts hour steady state. Same thing, but operating in different conditions, right? So we tried many different ways to measure the so-called similarity of this particular process with all other processes, right? And as you can imagine, this process will be very similar to this process. Everything same except the different operating conditions, right? So this is one of the similarity measures we have tried. As you can see, we can have this is a number between 0 to 1. Being 1 means the two processes are exactly the same, right? So close to 1 means the two processes are pretty similar. So this is just an example of how to measure the similarity. So here's a result. And if you just look at one of those figures here, the blue areas are where we can recover the data very well when you're missing a certain percentage of data. And x and the y are two very important parameters in the model. I don't think I want to explain those specific technical details, but essentially those four figures show if we have less than like 10% data missing for each process, 7,000 each numbers. If we have less 10% data missing, get intentionally removed, we can recover those data very well. Blue means we have a error like less than 5%, right? And if you have less than 1% or 5% data missing, we can easily recover those missing data. But if you have more than 10%, like 20% data missing, the area, the parameter choices that to allow us to recover the data very well become very small. That means on average, we might not be able to get a very good performance for the model. So this tells us for that particular data set that we are working with, if you're missing less than 10% data, our best link prediction model can help us to recover the missing data at very high accuracy, less than 5% error. Right? 5% in doing life cycle assessment is a pretty good number already. So that's the first example, and second one is look at the impact assessment, the second stage, the third stage of life cycle assessment. We use neural networks as a way to do this. So just to give you some background as well, in impact assessment, we convert all the emissions, resource use into three big categories of impact: human health, ecosystem health, and resource depletion. Right? So human health essentially means those emissions get released to the environment. What is the impact on our human health? On average, ecosystem health, the same thing, right? So here I only focused on just tell you the work we worked on the ecosystem health piece. Right? We are currently still working on the human health piece, but the ecosystem piece we have some result to show. So essentially, this ecosystem health is also called ecotoxicity, and in life cycle assessment, the people use this use-tox model, which is developed by US EPA to estimate all sorts of emissions, mostly chemicals, that impact on human ecosystem health. So in use-tox, they have more than 3,000 chemicals in this model, in this database. And there are about 2,500 chemicals in this database have this so-called ecotoxicity characterization factor, meaning they know in the use-tox model, they know what is the impact on ecosystem health for those 2,500 chemicals. For the rest, they don't know, right? And beyond that, we know that there are many more chemicals we use every day, right? 85,000 chemicals in U.S. EPA Toxic Substance Control Act, and beyond that, there are many more that are not in this act, right? So, and for those chemicals and many more beyond this circle, we simply don't know their environmental impacts and also human health impacts, right? So how do people know the environmental impacts for those chemicals? Or they do experiments, right? Essentially, the impact on ecotoxicity is a function of three factors, right? Fate factor, you release chemicals to the environment. How is that being transferred and converted into different medium, water, soil, air? An exposure factor, this is a measure to see how much in terms percentage of those emissions, chemicals released to the environment are being observed, being exposed to the species, intake species. And then lastly, effect factor for the amount of the chemicals I took into my body or into species body, how much of that actually have an impact on your health, right? So essentially it's a percentage, 3 percentages multiplied together, right? Those two, first two, fate factor, exposure factor, you have a relatively easier way to get those numbers. There are many physical, chemical models to do that. So last one is the most difficult because you have to deal with animals. You have to actually observe how much chemicals it needs for animals in a controlled environment to die. Like this, essentially, it's called SC50, hardest concentration. This is it's a mouthful here, but essentially you have a controlled environment, you're adding a specific chemical in the environment little by little, and see at what point half of the species in this controlled environment dies because of that addition of chemicals. Right? So in order to know this number, you have to have a lab, right? You have to grow animals, you have to buy chemicals, add into the animals and observe. So of course it's very time consuming, it's very expensive, so that's why we don't know a lot of chemical impact in the database set. So then our question here is, can we make use of existing data, which chemical impact on ecosystem health that we already know, to get this factor HC50 for other chemicals that we don't know, right? So in fact, there is a lot of already a computational approach to do that called QSA, which essentially just look at the chemical's structure, chemical physical properties, link that to the ecosystem health impact. For example, EcoSat, that's a particular model developed by US EPA. This model, this kind of model also have been developed from very simple linear models early stage to more complex machine learning based models these days, particularly using neural network models. So that's what I'm focusing on today. Okay. Right. So in the literature, there are actually people used neural networks to do this same kind of thing. But what they look at mostly are focused on a very specific species. A particular chemical impact on honeybees. Impact on particular types of fish. But in life cycle assessment, we want to know the average impact. So we need to know non-specific, non-species specific impacts. That has not been done, right? So neural network models, if you heard from the medium, deep learning, that's part of kind of neural network, has become very popular in the past couple of years. But actually, this is not a new thing. It has been around for many years. If you still write letters, physical mails, you write your friend's zip code, right? And the post officers, they recognize zip code, do not use their own eyes. There's a machine, right? The machine recognizes your handwriting later numbers and then classify your letter to different zip codes. That technology has been mature for a very long time. But the reason that neural network becomes, or deep learning, machine learning becomes more popular these days because our computational hardware capacity becomes very advanced, so that a lot of things that cannot be done in the past can be done today. So it's a neural network. Essentially, you have some inputs variables and also have an output variable which you want to predict or estimate. And in between, you have different layers of a neuron, like in our mind. And this model can be very complex. Have one layer and multiple layers in between. Here it's just one layer, right? In machine learning community, they have this principle called Awesom's razor, which simply means all other things being equal, the simplest solution is the best, which is essentially just to avoid this so-called overfitting problem. You can make the model very complex and you can get a very high accuracy of recovery, but which might not mean the best solution. So all other things being equal, the simplest solution is the best. So that's a principle we want to use here. So in our work, we build a very simple, the simplest neural network, just have one hidden layer. And in the input side, that's a sort of physical chemical properties for the chemicals in the ecotoxicity model. Like they have 11 physical chemical properties for each chemical. Upper layer is essentially that HC50 number we want to estimate. As long as we can estimate this number, the effect factor, the characterization factor can also be calculated. Right? Then in ecotoxicity, the model, the database we working with has 2,500 chemicals have that HC50 value, right? And then for each chemical, it has 11 physical chemical properties like this. So our model, to have optimize the model, our task essentially being divided into two. First, how many what we call features, those input variables we need to use. We might not necessarily need to use all the 11. All the 11 features used might not give us the best outcome, right? There's a selection, optimal selection. Second, in this network structure, how many, because we only have one layer, but how many nodes in this one hidden layer do we need? Right? That's two specific questions we want to essentially to do in order to have an optimized model, best model. So what we did is, similar to the previous example, we took all the chemical data in ecotoxicity which have HC50 values and split into two pieces. One is called test data, another is training and validation data, 70% versus 30%. And train our model only use the test data, training data, and essentially just try different number of neurons in a hidden layer and try to find the best one, right? After we found the best one based on the training data and the validation data, and then we use the model we found, which we thought is the best, to test the outcome, the performance using the test data. Right? So, we only use the training data to develop model, and the test data being set aside as independent. So now we can use the test data to actually evaluate the performance of the model. If the model performance, the test, R square is good, or better than whatever we have in the past, then we thought this is a better model. So here we use the most advanced model, so-called ecotoxicity model developed by US EPA as a benchmark. If our model is better than ecotoxicity model, then we can use our model to predict the other chemicals in the data set which do not have that HC50 value. So this is a result. Simply, our test R square is 0.5. As a comparison, the most advanced ecotoxicity model by US EPA has less than 0.2 R square. So obviously, our model is better than whatever is available right now to the community, right? So then we can use this model, our developed model, to estimate those chemical HC50 value for those chemicals in a data set which we didn't know before, right? And one more thing I want to mention that for as long as we have a model, you can get a number for any chemical that we didn't know their HC50 value, right? But we need to give user evaluation of accuracy, roughly, right? So we because we get the model based on a set of training data, right? A data set, we already know. So we can look at a new chemical which we need to estimate their HC50 value for, and to see how similar that new chemical is to the chemicals we used to develop our model. If they are similar, that perhaps means whatever number we get for the new chemical could be trustworthy, because it's similar to whatever we worked in the past. But if it's different, very different, that means even though you can still have a number for that new chemical, but that number might not be very accurate. So we use principal component analysis as a way to compare the similarities of chemicals. So on this map, you can add each dot or each circle represent a particular chemical, and you can find a central of all the chemicals which we used for developing our model, and we can draw a circle which includes, for example, 90% of the chemicals in our training data set. And for a new chemical that we want to estimate their impact number in the future, if that chemical is located outside this circle, which we call the application domain, which perhaps means even though you can still get a number for that chemical, you need to use that with a lot of caution. But if your chemical is located inside this application domain, we could perhaps say you could roughly trust whatever you estimate the user model. Right? Of course, this example and the previous example, we use those computational and data-driven approach to get a number, but our goal is not to replace primary data collection, right? But those estimated numbers can be used as a placeholder when the more accurate and more primary data becomes available. So some of our ongoing work we are doing right now, for the first example, lifecycle inventory data, we are developing other link prediction models for other popular databases. So we only worked with one particular database, but there are many others. For example, something called GREET, which is a database only for transportation-related things. And also we explore other applications of other models. Computation models. For the impact assessment data, the example I showed you is only for ecosystem health, the impact on species. Right? So the data we know for impact on human health is more scarce. Why? You can imagine, you need to work with people, right? And then you have much less access to health data. So we're working on develop other neural network models for ecotoxicity and also for human toxicity characterization as well. Right? So to just quickly summarize some key points I want to make today. Life cycle assessment, as earlier I introduced life cycle assessment, I think it offers a lot of valuable insights for environmental policy making at different levels. And the second, to do actual life cycle assessment in the real world is very data intensive. But luckily we have a lot of advancement in data science community which can help us to develop computational data-driven models, approaches to estimate some of those missing data. So with that, I want to thank all my team members in my group and also our funding agencies for the support of our work, and also thank Professor Lee and the center again for inviting me here. Thank you. Thank you very much. There are many ways to explore their correlations. Right? Essentially, we want to just use least amount of input variables which can represent the whole system. And of those 11 variables, some of them are very highly correlated. Meaning, if you use one, you don't need to use another. Right? So we. But
you have like 2,500
data sets.
So that's
data points.
I don't know how. I'm just curious how you handle because different chemicals have different properties too. So how you come down with that 11?
Oh, for each property, you have 2,500 data points,
Yeah.
right?
Okay.
For another one, you have another 205 data point. We simply, the simplest way is just to compare the correlations, right? And if you find that are highly correlated, you probably just need to use one. And in the machine learning, field, they have other, computer science-based approach to help us to get the best combination of parameters. We use many different tools, not a single one. And also, this is essentially a trial and error process. You try different ways and do the model and see if it's better or not. And eventually, we found we used 7 of those properties for our model. Right. And those 11 are only whatever is included in the ecotox, the database we are working on. But as you know, every chemical has much more properties than 11, right? So the one thing we're working on is to use other additional properties to see, we can add some new properties in there, can make the model better. Yeah. Thanks.
Yes.
Excellent talk. I think, by nature, I think LCA is quite similar to another EIA. I think that's based on one is about project, this one is about the product.
Yep.
And but I think for EIA and LCA, both of them, they have some difficulties. For example, the missing of data definitely is one of the difficulties. I think you give a very good example of how we can have some prediction about the missing data. And another difficulty about, sometimes for the two products or two alternatives in EIA, it's about, they may not have the similar same emission regarding all environmental impact. For example, one product could generate about 50 gram BOD per gram of product. But another product maybe can generate about 1 gram phenol per gram product. So one is about oxygen consumption, another concern is about the toxicity.
Right.
So how we can compare these two in the reality? Any comments on this?
Yeah. So in LCA, we also have a lot of those kind of occasions, I guess. As I showed earlier in that diagram or process of doing LCA, the last step is impact assessment, right? So in the previous step, the inventory analysis, you have 2 different process chains and have very different emissions, waste. But at the last step, we convert all the emissions into 3 big categories, impact categories: ecosystem health, human health, resource depletion. So even though you're for that BOD, for example, one product has 50 gram, another has 0.005 gram. At the end of the day, we convert everything, including not only BOD but all other emissions, possible emissions, into those 3 big impact indicator categories. Right? In that way, we kind of normalize everything together as the same impact, so then you can compare. But if you want to just compare those 2 specific impact because of BOD, of course, that's another story.
Okay.
Yeah, again, in relation to that question and coming back to the title of your talk, so the term of environmental footprints. Can you specify a few typical environmental footprints?
Right. The most popular one being carbon footprint.
Carbon.
Right? So carbon footprint essentially means during the life cycle of something, using this paper, buying this, doing this pencil, how much greenhouse gas emissions we generate from raw material acquisition to end of life. And also increasingly popular is water footprint, very related to the center. Water is a carbon footprint is more popular because greenhouse gas emissions has impact on climate change, which is a global impact. It doesn't matter where you generate the greenhouse gas emissions. In China and US, it's the same. But for water, it's a very localized resources, right? In water abundant areas, you use 1 liter of water, it doesn't matter too much. But in a water scarce area, use 1 liter of water might mean a lot, right? So in water footprint analysis, it's more complex. People need to identify where the water being used or water being polluted. Location matters. And second, the types of water also matters. Like if it's rainwater or groundwater or surface water, also matters different. What else? And there are many footprints, like even land footprint, right? So we consume products. Those products being used, being produced in another place. How much land did it use, right? So that's another kind of footprint. And also increasingly there are a lot of those social indicators being used in the footprint community. Like there was a recent paper in our journal called bad labor footprint, right? Meaning we buy some stuff from, for example, Africa, right? To produce that stuff in life cycle, they might use child labor. They might use, exploited labor. So, and then if you know the data, you know enough data, you can quantify how many child labor hours being used to produce the thing you consume, and then you can quantify that from life cycle, from a footprint perspective.
Yeah, I have another technical question before ask audience. How is this reproducibility of this kind of assessment? If it's conducted by different teams,
right?
The result arrived would be similar. Have anyone studied this? And,
yeah, that's a very good question. So, if you remember, I mentioned, because of the data-intensive requirements, we have to, the first step of doing life cycle assessment is goal and scope definition. So you define your goal, define your scope. So that's where this can become very, subjective. A lot of people, one group did this because of whatever data they have access to, they might define the scope in a very specific way. Another group looking at the same product, but they can perhaps define their scope in a little bit different way. Right? So the reproductivity of those kind of research, first, I guess you need to really understand how people define their scope and goal. So that's why there is a very high bar for documentation in this kind of work. People always want to other researchers to have very clear documentation of the whole process. What kind of process you include, where do you get the data, etc.
More questions from the floor? Yes. Wait.
All right. Thanks very much for a very interesting presentation.
Thank you.
I just want to ask whether you have considered in your data analysis, any interaction or independence between of the data sets between the 11 variables.
Right.
And my second part of the question is, have you tried to test the implications for the final accuracy of your model by differentiating the nature of the missing data? For example, you can have the missing data of the whole data set in the data cohort, or you could have the missing data by type of the same data sets in the cohort.
Yeah, very good question. The first question answer is yes. So we know that so-called feature selection process, selecting 7 out of the 11 variables, is a way to look at the correlation interdependencies. Right? So the second question is a very, very interesting, very good question. So we have submitted a paper based on the second example I mentioned, and the first round of review, one of the reviewers asked exactly the same thing. Maybe it's you, right? Anyway, we didn't consider that too much. But right now we are trying to categorize types of missing, occasions and see whether they have a different performance for the model. That's something we're currently working on. I don't have any result to tell you right now, but it's a very good point. Thank you.
Okay.
Any more questions? Well, I may take the liberty to ask another question. Is how you deal with data, value data coming from different sources? In a place like Hong Kong,
Yep.
we don't really produce a lot of data, but we can collect data.
Yeah.
For example, from China and the U.S., come from different sources, fill into different columns, different rows.
Right.
And how to deal with, they really come from different sources. The value can be quite different.
Yep.
And how you formulate a more complete set of data.
Right. So that's a very good question. So first, that's the different source of data. That's exactly why we worked with established database, that eco-event thing I mentioned earlier. So that database was developed by dedicated groups in a very long time. They're collecting data from all sorts of different places, and they have a quality control procedure before the data can enter to their database. So in that process, they kind of take into consideration of those the variations of same data from different places. So that's the best that we have. Right? So that's the first reason. Secondly, doing this sort of life cycle assessment, there are different types of life cycle assessment depending on your research question, but mostly from an academic point of view, we are more interested in the average, right? Average impact of this glass versus a plastic bottle, right? So the sources, the same data point from different sources, like produce electricity from Hong Kong, from mainland China, from other places. We are interested more in average, right? So that's why we did the pre-processing of that big data set shrinking into a smaller one. We just get rid of those location-specific data and just keep the one average number. So that, of course, does not help for people who do very specific life cycle analysis studies to look at the same product produced from different places, but helps other people.
Okay, I have time for one more question. Yes, please.
Thanks, Professor. I'm wondering that you mentioned about the missing data, and you also mentioned in the first part the link prediction. You say that less than 10% data you can cover it quite well. And I'm wondering, how about the unequal distribution of the data? Maybe just a lot of data missing in just that 10%.
Right.
Yeah, and then also it is a footprint, so it's step by step. Do you think the time or the time sequence will influence the prediction?
Okay, first question. For example, the 10% missing, it just means 10% data are unknown, right? And the distribution, so that 10% is an average. So we intentionally remove piece of data from the top, from bottom, and anywhere. Just randomly repeat those processes for many times. So that accuracy measure we got is on average, right? So in reality, in practice, it does matter in terms of distribution of the missing data, right? If you miss first 10%, you might have a very different result versus missing the bottom 10%. So we haven't done too much in that area yet, and that's something we have in mind. Very good question, thank you. Can you remind me of the second question? Sorry.
The time sequence of the different footprints.
Right. It does not matter too much because, as I said earlier, we care about the average, right? So life cycle assessment, you can do that in a very accurate way if you have enough data. And of course, the ideal case is produce something in the past versus producing something today. You might have a very different same thing. You might have a very different environmental emissions, resource use. But now, and the field is still far away from that kind of specific questions. So at this point, we don't care too much about that. Yeah, thank you.
Okay, one last question. Yes.
Follow-up question. On the slide when you show the model accuracy, when you have different percentages of missing data, the x and y axis is this distance and number of similarity processes, right? What do they mean?
Okay.
I think that's what maybe similar towards the question of what kind of data we are missing.
No, that has nothing to do with that question. So x is how many most similar processes you want to use to estimate the data, the missing data. So we have like 7,000 columns, right? That means you have for each process that misses data, you can have a similarity of that process with the rest of 7,000 plus processes, right? We do not need to use all the processes to calculate that missing data. Perhaps you only need to use the top 100 most similar processes, right? So the x is that number, right? Y is a parameter to calculate distance, a similarity, right? So there are many ways to calculate, a process similarity versus another process similarity. You can imagine that two vectors. Right, two vectors, essentially, it's a high dimension space. You can have a distance of those 2 points in a high dimension space. And then that y variable is essentially just a way to calculate the distance of those 2 data points in a high dimension space. Yeah.
Thank you.
Thanks.
Okay, thank you. Time is up. We have a very, very good discussion already. Certainly, it's to me, it's a challenging topic, challenging talk. But I hope you agree with me, and we learned something, and it's kind of rewarding. And by the end, again, please join me. Thank the speaker for the wonderful seminar.
Thank you very much.
And thank all of you for coming.